Okay, another feature of a graph that we're going to look at is symmetry. We're going to look at different symmetries of graphs. Not every graph is going to have a symmetry, but when it does, it can be very useful. All right, so symmetric about the y-axis. All right, so let's look what it says, and it'll be clearer when we look at a graph. A graph is symmetric about the y-axis if for every point xy on the graph, negative x, y is also on the graph. So basically, what we're saying is that it would look something like this. If you have a point x, y on the graph, then you're also going to have the point that's the same distance back in x, so negative x, y. So maybe something that would look like this. This would be a graph which was symmetric about the y-axis. In other words, it's a reflection over the y-axis. It looks the same when you flip it over over the y-axis, right? And if we want to check to see if something has that symmetry from an equation, basically what we do is we check to see if using negative x and x gives us the same equation. For example, if I want to check if the graph of y equals x squared plus 2 is symmetric about the y-axis, all right, so I have y equals x squared plus 2. Now, I want to try negative x for x, all right? So I'm going to say y is, and I'm going to put negative x in anywhere x is. So negative x squared plus x. But when negative x gets squared, I get x squared. And so I get x squared plus 2, which is the same as the original. So I know it's symmetric about the y-axis because I used x and negative x and they gave me the same thing. So if that was over the y-axis, what would happen over the x-axis? All right, let's take a look at that. So now a graph is symmetric about the x-axis if every point xy on the graph, x minus y is also on the graph. Okay, so this time I have x, which gives me both y and minus y. Okay, so, well, this x point is actually not on the graph, so let me get rid of that, sorry. Okay, so I have x, y, and x minus y for the value x. So something like this would be symmetric about the x-axis, okay? Because, look, it's a reflection about the x-axis. It looks the same on top and on bottom. And that's another way of saying that if x comma y is there, then x comma minus y is there. So not surprisingly, we're going to check in a similar way. This time, we're going to use negative y in for y and see if we get the same equation. So x plus y squared equals 1. Is this symmetric about the x-axis? All right, so I have x plus y squared equals 1. So I'm going to try minus y for y everywhere. So x plus minus y squared equals 1. Then I'll simplify. X plus, but minus y squared is y squared equals 1. That's the same. So since I replaced minus y for y and got the same thing, this is symmetric about the x-axis. So let me just make note that if we had had something like, imagine we had x plus y cubed equals 1, and we did the same thing, and we tried negative y in for y, I would get x plus negative y cubed equals 1, and I would get x now minus y cubed equals 1, which is not the same. So in this case, it would not be symmetric about the x-axis. Okay, so there's an example where it wouldn't work for that one. All right, so we replaced negative x with x for x in one case and negative y for y in one case. What if we did them both at the same time? So symmetric about the origin. Well, that's what we're talking about here. A graph is symmetric about the origin if for every point x, y on the graph, negative x, negative y is also on the graph. So something would look like this would mean if x, let's call that xy, is on the graph, then negative x, negative y would be on the graph. So here's a graph that would look, well, it doesn't look so great there, but that's a graph that would basically be symmetric about the origin. Okay. An interesting thing to note is that being symmetric about the origin, so I replaced x with negative x and y with negative x, it's not actually definitely going to be symmetric about x or about y individually, but essentially what it has been is it's like doing them in sequence. So it's as if I took the piece up here and I flipped it over y and then flipped it over x, and so by doing one and then the other, I get symmetric about the origin here. But in the end, it has neither of those individual symmetries. It could, but it doesn't have to. All right, so back to symmetric about the origin. So what I'm going to do is I'm going to use negative x for x and negative y for y at the same time and see if I get the same equation if I want to check an equation. For example, y equals 2x plus x cubed. Is it symmetric about the origin? Well, y equals 2x plus x cubed. So I'm going to try negative x for x and negative y for y. So that would give me negative y is 2 times negative x plus negative x cubed. And I want to see if I can get back the original equation. Negative y is negative 2x minus x cubed. Okay, it doesn't look like it yet, but realize I could basically multiply both sides by negative 1. I'm allowed to do that. And so on the left, I'd get y equals 2x plus x cubed, which is the same as my original. So I was indeed able to get back the original equation after substituting negative x for x and negative y for y. So this one is symmetric about the origin. So in each case, you make the proper substitution and you see if you can get the original equation back. If you can, then it is symmetric in that way. If you can't, well, then it doesn't have that symmetry. Just a side note here, can we think of any graph that has all of these symmetries? Well, we actually just saw it. Realize that a circle centered at the origin is symmetric about the y-axis, it's symmetric about the x-axis, and it's symmetric about the origin. That particular graph is nice. It has all of those symmetries, but that's rare. But just an interesting side note.